All right, today we're talking about the bedrock of all rational thought, propositional logic. And no, this isn't just some abstract theory. This is the precise, hidden language that powers, well, pretty much everything, from math and computer science to how we build solid arguments in our everyday lives. So let's dive right in.
So let me kick things off with a classic brain teaser, one that really shows you just how messy our everyday language can be. What about the sentence, "This statement is false"? Go ahead, think about that for a second. If the statement is true, then it has to be false, right? But if it's false, well, then that makes it true. It's a total paradox. And that is exactly why we need a different kind of language, one with super strict, unbreakable rules. Okay, so here's our game plan for today. We're going to start with why we need this precision in the first place. Then we'll get into the basic building blocks, which are called propositions. After that, we'll look at how to connect them, how to check their truth with something called a truth table, and finally, we'll wrap up by looking at why any of this stuff actually matters in the real world.
You know, when you're working on a mathematical proof or maybe a social science model, there's just no room for words like maybe or kinda. Our everyday language is just full of that stuff. It's ambiguous. But logic demands absolute clarity. Every single statement has to have a precise, verifiable meaning. That's the foundation we're building on.
All right, so if we're going to build this language of pure reason, we have to start with the most basic element, right? The foundation. I want you to think of these as the individual bricks. You know, the things we use to build up these huge, complex arguments. And these fundamental bricks, well, they're called propositions.
So what exactly is a proposition? Here's the most important rule. It's any statement or assertion that can be definitively labeled as either true or false. And that's it. There's no middle ground, no sort of. It's a completely binary yes or no world. So it is raining outside, that's either true or it isn't. 2 + 2 = 4, that's verifiably true. See? Both of those are propositions. Here's a perfect example to make this super clear. Let's take the statement 3 is an odd number, and we'll just call that P. We can all agree that's true, right? Easy. Now, how about Q? 27 is a prime number. Well, a quick check shows it's divisible by 3 and 9, so that's verifiably false. The key thing is both P and Q are clear, unambiguous propositions. One's true, one's false. Okay, so we've got our bricks, our propositions, but you can't build a house with just a pile of bricks, right? You need something to hold them together. You need mortar. And in logic, that mortar comes in the form of what we call logical connectives. These are the tools, the operators, that let us combine our simple statements into much more complex and interesting ones. So here they are, the 5 fundamental tools in our logical toolkit. We've got negation, or not, which just flips the statement's truth value. We have conjunction, or and disjunction, or, which are ways of joining statements. And then we've got the 2 that can be a little trickier, implication, which is our classic if-then, and by implication, if and only if, or if for short. All right, let's start with the absolute simplest one, negation or not. Its job is super easy to understand. If our proposition P is true, then not P is false. And if P is false, then not P becomes true. That's all there is to it. It's basically just a logical on-off switch. Next up, we have conjunction, which is just our fancy word for and. Now, you can think of this one as a really strict gatekeeper. For the combined statement P and Q to be true, both P and Q have to be true. No exceptions. If even one of them is false, the whole thing is false. It all comes crashing down. Okay, now for the famous one, implication, or if P, then Q. This is where things can feel a little weird, a little counterintuitive at first. Just stick with me. An implication is only considered false in one specific situation, when a true premise leads to a false conclusion. You can think of that as a broken promise, right? If I promise, if it's sunny, then I'll go to the beach. The only way I've lied is if it is sunny and I don't go. In every other case, the logical promise is considered kept. All right, we've got our bricks and we've got our mortar. Now it's time to actually be the architects. We can start combining multiple propositions and connectives to form these bigger compound propositions. And the blueprint we use to figure out the truth of these complex structures, that would be the mighty truth table. Now, just like in your old math classes with PEMDAS, you can't just do things in any random order. Logic has its own order of operations to make sure everyone gets to the same answer. We always start with anything inside parentheses. Then we apply any negations. After that comes our ands and ors, and finally we tackle the implications and by implications.
Okay, let's actually see this in action and build a more complex truth table together. So we always start by listing out all the possible combinations of true and false for our basic propositions, P and Q. Then we just solve for the little pieces, following our order of operations. We figure out P implies Q. Then we figure out not P. Then we combine not P and Q with an OR, and for the grand finale, we connect those two main results with the by implication. You see? It's just a systematic, step-by-step process that gets us to that final column.
Now, this is where things get really cool. Once we start building these complex statements, we begin to notice some really fascinating patterns. It turns out some statements, no matter what truth values you plug in, end up being logical certainties. And others, well, they're logical impossibilities. And these special cases have names. They're called tautologies and contradictions. A tautology is a compound proposition that is always true. It's structurally true. It's impossible for it to be false. A contradiction, as you might guess, is the exact opposite. It's a statement that is always false. It's a structural, logical impossibility. So here's a classic example of a tautology. P or not P. I mean, this one just makes intuitive sense, doesn't it? A statement has to be either true or not true. And if you look at the truth table, it proves it out. It doesn't matter whether P starts out as true or false, that final column is always, always true. And now for the flip side, a classic contradiction. P and not P. Again, this is a logical impossibility. A single statement just can't be both true and false at the exact same time. And, just like before, the truth table confirms it for us. The final column is all Fs. This statement is structurally false, and it can never, ever be true. Okay, so we've built this whole beautiful, precise system with our bricks and mortar and our truth table blueprints. But you might be asking, so what? What's the actual point? Why does mastering this formal system of logic really matter once you leave the classroom?
Well, it matters because this is the hidden engine that drives all rigorous thought. When an engineer designs the circuits in your phone, the logic gates are literally performing these operations, and or not. When a scientist sets up an experiment to test a hypothesis, they're using this exact logical framework. Anytime anyone, anywhere, builds a valid mathematical proof or a sound argument, they're relying on these very principles, whether they know it or not. Which kind of leaves us with one last, really fascinating question to chew on. We have this perfect, clean system for building valid arguments from a set of assumptions. So why is there still so much disagreement in the world? Could it be that the problem isn't in our logic, but maybe in the basic propositions we choose to accept as true in the first place? That's definitely something to think about. Thanks so much for tuning in.